All right, so let's try this out. Let's get rid of that. Trying a different format because the video quality was pretty poor through Teams. So we're going to see if this method works a little bit better. What we're going to do today is I wanted to re-record because I lost audio in my last one after 20 minutes. Go figure. But wanted to go over base curves in like a really 30,000 foot overview. Most of what we're going to cover is our readings. Like, for example, the proper base curve is going to eliminate a whole host of different monochromatic aberrations, oblique astigmatism, and whatnot. I could put a -3 on virtually any base curve. I could put it on a plano base and put plano with a -3 on the back. That's a -3. I can put a +6 base curve on the front. +6 with a -9 on the back. That's a -3. Hell, I could put a +12 a 12 base curve and put a -15 on the back. It's still a -3. Arguably, I could put a -3 base curve on the front and a plano on the back. Optics would be all wonky. It's take your glasses, and if you have relatively similar prescriptions and axes and right to left, take it this way. I'm a -125 SIL, both eyes. I can see relatively well straight ahead, but off to the edges, it is awfully wonky. Well, that's sort of what your patient is going to experience if you put them in a base curve other than the optimal one for their prescription. And now, what is the optimal base curve? Well, there are some very simple ideas. Let me just see if I can find. Open up. Don't know why that was not open. Perfect. So hopefully we're still sharing. So for the base curve selection, oftentimes we're going to see really simple things like this. This was from our OptiCampus, or you'll see the same type of chart in the systems book, the Brooks and Borish. But oftentimes you're going to have, like, it'll say, hey, I have a high plus lens, goes with this steeper front curve. I have a high minus lens. I have a very flat or minimally curved front surface. So like half diopter is way flatter than a very steep 10 diopter curve. And obviously, if you're starting very high minus, slightly less minus, it's a little steeper. A little bit less minus, a little steeper. Switch into the pluses, I'm at a 6 base. Start going a little higher plus, a little bit higher base. And all you can see this sort of transaction here, this migration from more plus gets me a steeper base curve, more minus gets me a flatter base curve, and all this is pretty straightforward. But if we get down to the brass tacks, this doesn't tell me, based on the sphere and SIL power that I have, what base curve do I pick out? And what it doesn't also take into account is, how about the material? How about the vertex? How about the working distance? And all of these may affect what base curve is going to be ideal to eliminate a series of these monochromatic aberrations. This is a chart that was shared with me by an acquaintance, a colleague, Brian Body, and he's actually come up with a handful of these different formulas that I'll throw into the reading based on whether it's a plus lens or a minus lens. Vogel's rule is definitely in our textbook in our reading and our homework, but this would be one where I'm going to take and magnify this bottom part. And if you can see, the higher plus you are, these +8s, +6, +2s, plano, -2, low myos, moderate myope, severe myope. What you're going to notice is the more minus we are, the flatter we're going. These down here are the planos, the half bases. The high pluses are the +10s. But what you'll notice is it's not just, hey, I have a -0.5, I'm going to go with a 6 base. It's based on the sphere and also throwing into account what's the SIL as well. Because remember, by throwing two different meridians and one's significantly more minus than the other, you arguably are going to need a flatter base curve the more minus SIL you have in there. So for example, if I had a -775 sphere or a -775 and go all the way down to here to a -175 SIL, this surfacing chart says, here's my -775, here's my -175 SIL. My chart from this particular manufacturer for this particular lens design, I'm going to grab my 2 base. But it turns out that using this particular formula or this chart, if I had a -775 and had a 2 or 225 SIL, I'm no longer going to need a 2 base. I want my half base or my plano base. Now, ideally, I would imagine that if you did any calculations out, it wouldn't be a 2 or a plano would be somewhere in between, but they had to round to the closest one, which is why ideally this almost may be like minus a plano, quarter, a half, 75, 125, 150, all the way up, and you keep going. Well, they're rounding to the clearest, the closest one that we have based on these increments on this particular manufacturer. So if I said I need a minus 550, let's do a minus 6 with a 3 sill. Well, ideally, you'd say that minus 6, I must be on a 3 or a 2 base based on this. But a minus 6 all the way with a 3 sill, they actually want this down here in a flatter base curve here. So let me focus in on this one, and we'll just do a little easier. Minus 775 with a 2 sill. The answer for this one, or if I were to do a surfacing chart and following the direction, I'm going to use this flatter base curve here. Now, here's another one, and these are in the high plus end of things. This is a +2 to a +7. Notice how the scale's a little bit different. As this goes down, we're getting more plus. Just a different way to look at it, different source, different surfacing chart. So again, high plus, I'm getting a steep base curve. A little bit less plus, a little bit less steep. I start getting into the +2s or +2s with a lot of sill. And now I'm getting into relatively flat base curves. And what you don't see on this is a computer program. This particular lens has an 8.5 base, a 7 base, a 750, a 4, a 3, and a 175. Well, the minus end of the spectrum for the contact lenses, for the eyeglass lenses, is simply not on this chart. We'd have to scroll up or down, but wanted to show you if we had this particular lens and had a +4 sphere, we put on a 7 base. If we had a +4 with a -75 sill, we put on a 7 base. But if we've had a +4 with a -1, this manufacturer for this material in this case would ask us to, in the drawer, get our semi-finished lens that we're going to surface and put a 550 base instead of a 7. Now remember, when we're doing the semi-finished, that means the front surface is already fixed. So here we have 4, 5.5, 7, or 850. Which base curve based on this prescription is going to be ideal? Now this is where we have to start putting our Sherlock Holmes hats on, and that is what that's not what I wanted there. That's not the right camera, but that's okay. We'll get rid of that. So just go to here. Sorry about that. Technical difficulties, I'll have to splice that out or just ignore it. So what's going to happen is, in this particular case, if I were doing problem shooting and I had somebody who had a -625 with no sill and an 8 base, and now somehow this chart got sent to the lab and they came back and the prescription was dead on, but they had just a little bit more sill, check your base curves, because oftentimes if there's a very mild prescription change, say a quarter diopter sill, and same lens, same lab, same material, same manufacturer, but all of a sudden you change the base curve by a diopter and a half or 2, that may be the key on why they're having difficulties. I don't, as a optician or as an optometrist, don't recommend designing my own lenses and putting my own base curves on there just for the heck of it or because some charts showed me, but it is great for problem solving after the fact. There's a lot of money that goes in to designing these. There's a lot of effort in engineering, and generally the manufacturer knows through ray tracing and through computations, and don't forget there's asphericity concerns. There's a specific base curve that should work the best for your particular lens design. But if it doesn't work and you feel that the base curve is altered enough and the prescription has not, that's when I would start looking at, hey, do I want to go back to a closer or similar base curve to what they were wearing? But if I went from a spherical CR39 to an aspheric polycarbonate, it may not be appropriate to match the base curve because the lens design is not warranted. Now, along that line, I wanted to show you my shirtings ellipse. This you'll see in a lot of times, but this is actually easier than it looks. And all I have is the lens power along the x-axis and the base curve or optimal base curve along the y-axis. Here, if I have a -7, well, I'm going to go -7, I'm going to go all the way up until I hit this here. Well, in this case, I'm in this blue box and I'm at a -2. Well, there's actually 2 curves on my shirtings ellipse. There's the Ostwald and there's the Wollaston. And it turns out to minimize certain monochromatic errors like oblique astigmatism, for example. Again, it's in the reading, and this is not going to be a 2-hour lecture, but just for the base curves. Here, there's a base curve around here that's going to be about 3 or so. So here's my -7. I'm going to follow this along. Arguably, that's about a +3 base curve. But there's also an area where all the way up here, if I run into this, there's a base curve that's probably going to be around +17 or so. Anybody who's in surfacing know, or if you've taken a base curve, we don't get base curves of +17. It's not practical based on the manufacturing we have for the frames and our edgers. So generally, anything that we're going to do along the shirtings ellipse for choosing base curves, optimal base curves based on my prescription, is going to be along this Ostwald curve. And so it's pretty straightforward. If I had a +3, well, if I follow this all the way up, it's going to ask me to, when I surface this lens, to use an 8 base. Well, it makes sense. The more plus, the steeper the base curve. The more minus, the flatter. And here's a pretty straightforward graphical representation of how we do this. But I wanted to point out something a little bit more in depth, and that is let me pause this for a second. I guess I won't be able to do that, but let me get my, and I'm going to bring up a cool, let me share anyway. So there's an absolutely cool spectacle optics program that you can get on OptiCampus. And this is actually tremendous because we get to play with all sorts of stuff. Geometric analysis. These are great because you can look at whether an image is inverted, magnified, real, imaginary. This is so much better than memorizing, but it's actually fantastic. There's some progressive analysis in here. There's just so many cool things. But for our purposes, we're going to go down to this shirtings ellipse. And what the purpose of this little exercise is, without getting into specifics, this is saying what the optimal Ostwald and Wollaston curves are based on, but there's a handful of things because it turns out that we're going to use 1375 for the vertex distance because this is what many of our phoropters, the manual says is supposed to be put at when we're refracting. But if I change this based on how close or how far the lens is positioned, there's actually an argument to be made that based on how far away the lens is, it's going to alter what the ideal base curve will be based on where we interrupt here. Turns out that my working distance, if I'm doing something at infinity distance or if I'm doing something at close work or computer, notice how based on the lens design in this particular formula, this particular device, it turns out that if I wanted a object at distance, it's going to give me a different series of base curves. Now, if I had different materials, like a 174 high index, let's do 174 high index, notice how this is changing as opposed to a CR39. The whole curve to optimize the outcome. So again, vertex distance, the index of refraction, the object, what you're looking at, there's a whole series of what's going to change is based on what the prescription is, all these different variables, and there's one specific area around here that should optimize. This is still not taking into account other things like the ray tracing they do, the level of asphericity in terms of how that affects the base curve. But this, I did want to show you guys this one based upon what we're doing, because the base curve question is something that's a lot more complicated than just, hey, this here. So again, this was just a brief overview on terms of how the relationship more plus equals steeper, more minus equals flatter, how surfacing charts will look if you're in a lab and you're actually doing surfacing, what a shirtings ellipse is with the Ostwald and the Wollaston, knowing that in almost 99% of the case that I'm familiar with and in my experience, we generally use this lower curve for practical applications and how our machines are set up. And then this particular curve can change based on a number of variables. So at any event, let me unshare this and take a look at you there. Very good. And that's pretty much it for today. I just wanted to, again, give a quick and dirty overview of the base curve process, but we're going to be basing more of what we're doing on the reading this time in terms of levels of aberrations, what these are fixing, understanding what lens design can't do in terms of there are certain monochromatic aberrations that are based upon your pupil size, and they're not really a big deal in terms of lens design. So we're going to go over that. And the chromatic aberrations, your lens design really isn't going to have that much of a impact on your ABI values or your chromatic aberration, your longitudinal or latitudinal chromatic aberrations, but there are a series of the monochromatic aberrations where proper lens design is going to be critical. And when we start problem solving, when it's appropriate to start matching or changing or altering base curves and when it's not. So at any event, that's just the once over, the quick and dirty. I appreciate it, and we'll see you guys in class shortly.